Homological 3D verisymmetry. Hopefully.
Yay.
Yeah. Thanks a lot for the invitation. I'm glad I finally managed to make it here. I want to talk about some bigger ideas, and in particular related to some work I did previously with Dominic Ayoto and Matt Balmore and Justin, and some recent and ongoing work with Justin and my grad student, Nick Garner, and a Davis postdoc, Mike Girassi, and a paper that should be out, hopefully, almost certainly before Christmas, or it's just not coming out, with Justin and my student Nick Garner and Alexei Oblomkov and Lev Rozansky. This sort of framework that our story belongs to has to do with twists of 3D gauge theory. Physically, it's 3D n equals 4 gauge theories. And more generally, I'd like to start out by just talking about the structure of topological quantum field theory in 3 dimensions. And so I think in this talk, I want to start out with some general properties of 3D TQFTs, and then try to explain how these properties and features are actually realized in 3D gauge theories. And maybe at the end, I'll have time to say a bit about applications and nice conjectures and constructions related to knot homology, which is what that last paper is about. And maybe I won't have time, and that's okay too. So let me start with cohomological TQFT in 3 dimensions. The sort of the prototypical model of such a TQFT is Rozansky-Witten theory. And so Rozansky and Witten considered what I will be calling the B-twist of 3D sigma models with a hyperkähler target. And then Kapustin, Rozansky, Salina wrote a follow-up paper in which they described a lot of the cohomological and algebraic structure that should exist in these sigma models. And that's really the thing I'm going to be trying to generalize to gauge theories and to A-twists throughout the talk. Before I get there, though, let me explain what I mean by cohomological TQFT. In my mind, coming from physics, I mean by this that there's an actual TQFT. Sorry, an actual QFT. There's an underlying quantum field theory, not necessarily topological, not necessarily T, with a differential. Usually coming from supersymmetry, that preserves, in a hand-wavy way, everything in sight. It preserves, it acts on everything in sight. It acts on operators. It preserves correlation functions. That's the same thing as saying that Q is a symmetry of the theory. And trivializes the stress tensor. in other words, practically, continuous deformations of spacetime the 3D spacetime manifolds are Q-exact. And then the cohomology of Q acting on various algebras and vector spaces and categories and I will make this more precise as we go on. Then the cohomology of Q behaves topologically. In other words, like a TQFT. So this should be familiar in various guises. The two-dimensional A and B models are the most famous examples of a TQFT of this type. The sort of features that you start seeing are that so in two-dimensional TQFT, boundary conditions form a category. In a cohomological TQFT, they form a derived or general A infinity category, and they're higher operations that one has to deal with, all coming from the fact that the actual theory is not topological but only cohomologous. Algebras of local operators get all sorts of higher operations from being cohomological. Sorry, I will also assume one more thing. That everything in sight, by which I mean algebras, categories, and so on, are at least Z mod 2 graded. Which physically comes from a notion of fermion number, and often things will be Z graded, such that Q has degree 1. So the main examples of theories of this type in 3D are two types. Sigma models, where the fields of the theory include maps from whatever three-dimensional space-time is into some target. And to be more precise, these are supersymmetric n equals 4 sigma models with complex symplectic target X. There are two ways to turn these into TQFTs. Very explicitly, there are two different differentials that one can take cohomology with respect to. This is, again, just like the situation in two-dimensional theories. There are A models and B models. If you have a Kähler manifold, you can define both an A model and a B model. And this same thing happens here. So these always admit a B twist. And I realize that at this point, saying A or B twist may not make any difference. I'll go on and explain what algebraic objects are associated to this in a second. So they always emit a B-twist. That's a 3D analog of the two-dimensional B-twist. And by always admit, I mean there exists a B-twist that makes sense on any three-dimensional manifold, any 3D curved spacetime. It's Z-graded if we can find a C star isometry of X for which the complex symplectic form has weight 2. And then one has to use this extra symmetry to lift this Z12 grading that's always there to a Z grading. So, for example, cotangent bundles are of this type. So if X is a cotangent bundle of some Y, then you just shift the degree of the cotangent fibers, or use a C star that scales the cotangent fibers, and you get something that's Z-graded. So continuing on with sigma models. Sigma model 2x admits a full A-twist. In other words, something that makes sense for any three-manifold, only under very restricted conditions. Only if X has a hyperkähler structure. Metric. And there's an SU2 metric isometry that rotates the P1 of hyperkähler structures. And that's extremely special. Sorry, it's the P1 of complex structures. Rotating twistor space. But one can define an A-twist on manifolds of a restricted type under more general or more relaxed conditions. So there's an A-twist. In other words, there exists such a differential on manifolds that look like surface times time, or in general have a transverse holomorphic foliation when this holds. So when you don't need a full SU2, it's sufficient to just have a U1, or in complex language a C star acting on X, such that the holomorphic symplectic form has weight 2. And the A-twist is always Z-graded. That comes for free. So that's the situation with sigma models. The things I've been interested in recently are not sigma models, but gauge theories, closely related.
Okay. So the SU2 symmetry examples, those are what? Just cotangent bundles to homogeneous spaces?
So I'm not sure that's good enough. There are some silly examples that come from cotangent bundles to cotangent bundles. So you take a real manifold, take its cotangent, and then take the cotangent of that again. Or in other words, it's 3 copies of the cotangent bundle of the real manifold, and there's an SU2 that rotates those 3 copies. Kapustin and his students wrote some papers about that about 10 years ago. More interesting examples are things like the Atiyah-Hitchin space. Atiyah-Hitchin appears for us as the Coulomb branch of pure gauge theory. These are more generally smooth monopole moduli spaces. End up having, so monopoles in R3 have this property, and the SU2 just rotates R3.
Okay.
But again, like so like T star P1 does not have this property. However, the singular space, if you take the nilpotent cone, that does. The resolution breaks this. Okay. So there's sort of examples type 2 gauge theories. 3dn equals 4. Gauge theories. And the data of the gauge theory is, for purposes of a quasi-mathematical talk, a complex reductive group G, and a symplectic representation that's of the form R plus R dual. Or the cotangent bundle of R, where R is just some linear complex representation. I can generalize gauge theory to pair it with sigma models. The nicest targets that I can put here are cotangent bundles of something that's not linear. And so that works as well. I'm, for now, doing this to keep everything simple. Effectively, this behaves like a sigma model to the derived symplectic stack. I guess I usually cringe a little when I say that, but I shouldn't here. So if you take the symplectic quotient but treat it as a derived stack, then a lot of the algebraic statements one would have made about sigma models extends directly to the gauge theory. And there's a very nice parallel, and sometimes you don't need to pay attention to the fact that it's a stack, and you just use it as an ordinary space. And this admits both A and B twists, and they're both Z-graded. So just for history, so I said a bit about the B twist. So this was Rosansky-Witten theory in the case of sigma models. The A twist in the case of gauge theories is also something familiar. It's a reduction of the Donaldson-Witten twist. And if one starts computing 3-manifold partition functions in the 3D A twist, one gets Seiberg-Witten invariance. I don't want to talk much about partition functions. In fact, there's nothing new that I can say yet. I want to talk about sort of the opposite side of TQFT. Not the global structure on three manifolds, but local structure. Algebras of local operators and categories of lines and boundary conditions. Again, to make an analogy with 2 dimensions, so the first things that people computed in 2D A models and B models were partition functions. And this gave rise to the Gromov-Witten invariants of Calabi-Yau's or period integrals. And then it was realized that there's actually interesting local structure. In the A model, there's an algebra of local operators, that's quantum cohomology. There's a category of boundary conditions, that's the Fukaya category, and there's supposed to be a fancy way to start with the Fukaya category or derived category of coherent sheaves and reproduce Gromov-Witten invariants or period integrals. Anyway, I want to talk about sort of the category side of these firsts. So what algebraic objects do we have? In dimension 0, by which I mean physically operators of dimension 0, in other words, local operators, this is the thing that in TQFT formalism, the TQFT assigns to the two-sphere. It's the two-sphere because S2 is the link of a point, which is where the local operator sits. So this has the structure of an E3 algebra. Which I won't explain here, but I will say that its Q cohomology, which I can note A, this is the cohomology of ops, which is some DG vector space that Q acts on, is a graded commutative Poisson algebra such that the Poisson bracket has degree -2. There's, just to connect with physics, there's a cool construction in field theory of this Poisson bracket that I like. Topologists, well, homotopy theorists and TQFT people have been telling us for a long time that this Poisson bracket exists, and in Rosansky-Witten theory, it should be the same thing as some Poisson bracket of functions. There's a direct physical construction of this Poisson bracket that I talked about in a paper with Chris Beam, Matt Bullimore, Andy Knightsky, and David Bensky. So physically local operators are things supported at points, and the brackets of two local operators, O and P, is obtained by putting the local operator P at a point, surrounding it with a two-sphere, and integrating the second descendant in the sense of Witten's topological descent that he used in Donaldson theory. So one can use topological descent to turn local operators into forms, and you turn one of these into a two-form and integrate it around the other one. This is, and then you shrink this down, and it defines a new local operator, and that's the bracket. Also, once you have a commutative or graded commutative algebra, you can take its spec. And this is a way to define a moduli space in a TQFT abstractly. So the spec of A is, by definition, the topological moduli space of vacuum. So now let me give you examples. Basic one is the B-twist. So let's do sigma models to your cotangent model. So in the B-twist, this algebra ends up looking like Dolbeau zero anything Dolbeau cohomology of X, or algebraically it's cohomology of the structure sheaf. And first, this is the 3D version of saying polyvector fields, and it in particular contains functions on X. The interesting cases are when X is non-compact, then functions on X is very large, and the bracket defined by this TQFT procedure is the natural Poisson bracket induced from the fact that X is complex symplectic. The bracket is the bracket. In the A-twist, this algebra is much stupider, or much smaller. It's Durand cohomology of X. It's the same thing as Durand cohomology of Y. The product is not deformed like it is in 2 dimensions. So it's not quantum cohomology or anything fancy, it's just cohomology. Okay. In gauge theory, the B algebra already starts to get more interesting. So here we have a group G and some representation R plus R dual. In the B twist, the most compact form to describe this is as functions on that derived stack. And maybe, and I should throw in a little shift. And spec A is essentially what physicists call the Higgs branch. It can have a few extra decorations from the derived bits in here. This is I think this is the cleanest mathematical definition of what the Higgs branch of vacua is in a 3D theory. So things to say. If the representation is faithful, then you can ignore all the derived structure and this is literally just functions on the symplectic quotient. If the representation is not faithful, then extra stuff arises. Extreme example, if you take pure gauge theory, meaning that the representation is trivial. So, example, you have any G, but trivial R, and you compute this thing, you find coming from the fact that the moment map in the symplectic quotient has to be implemented in a derived way, you find an algebra generated by some Grassmann variables that are valued in the dual of the Lie algebra shifted by 1. Take G invariance of that. Physically, these are gauginos. And what I'm saying is that if you B-twist pure gauge theory, there will be gauginos in the algebra of local operators that sit in there. And mathematically, another nice way to describe this is as the de Rham cohomology, or any sort of homology or cohomology of the group, which will become important in a second. Now, in the A-twist, things are functioning. The only complete mathematical description of this algebra of operators is from the BFN construction. This is Braverman, Finkelberg, and Nakajima. It implements a sort of state operator correspondence. The details are more subtle than that. So let me just write it down, and I'll say some things about it. So I'm going to let D be the formal disk, the thing whose functions are Taylor series, and D star is a formal punctured disk, the thing whose functions are Laurent series. And there's a space that I think after Joe Kamnitzer really like to call the raviolo. I think Justin and Phil and others are really advocating the bubble. So want to consider two disks glued over a punctured disk as a scheme. So schematic picture of this, I guess some people also call it the UFO. So we have two disks that are glued everywhere except the origin. This is an algebraic version of S2. It's the S2 that surrounds a local operator. And in a physical state operator correspondence, you would want to say that operators sitting in the middle here are the same as the Hilbert space obtained by quantizing the theory on S2. Here, the raviolo, and one can implement, again, there are subtleties, but one can implement an algebraic version of that. And the answer looks as follows. So we'll, to find that Hilbert space, we build a classical phase space. In this case, it'll be solutions to BPS equations on this double disk. Algebraically, it's maps from the double disk about lower the bubble, into R mod G, and this is where subtlety comes up. It should really be the cotangent bundle, but it suffices to take half of it. So what do maps from the double disk into R mod G mean? This is G bundles and sections, algebraic sections of an associated R bundle on two disks identified over the punctured disk by a singular gauge transformation. So by a gauge transformation, that lives in the algebraic loop group. It's gauge transformations on the punctured disk, meaning G, but defined over formal Laurent series, matrices of Laurent polynomials. So allowed to have a singularity at the origin, and this is modulo gauge transformations on the two disks. Okay, that's a handful. This is, however, a space that has now been analyzed in great detail in many ways. And the actual algebra of local operators in the acres in gauge theory shows up. Naively, it would be Durand cohomology, but because this is infinite dimensional, one has to be careful. And the right thing, at least mathematically, turns out to be Burrell-Moore homology of this space. Okay, so physics comment. This is a really hard thing to find in physics as well. There are monopole operators that show up in 3D gauge theory and physics, and the monopole operators are in here. Monopole operators in physics are labeled by co-characters of the group, magnetic charges. And the monopole operator of co-character lambda corresponds to the fundamental class of, it's really the orbits, but it's a fundamental class defined by setting this gauge transformation to be z to the lambda. In other words, some diagonal matrix with singularities. The product is convolution. In other words, if we want to multiply two of these local operators, we should collide them, which means stacking the disks. And that induces a convolution product in cohomology. And then once one understands this thing, which is surprisingly computable, spec of it is the Coulomb branch. So there's a thing called the Coulomb branch in three-dimensional gauge theories, and this is the mathematical way to get it. The Coulomb branch is large and interesting whenever there's a gauge theory, whenever there's a gauge group. In sigma models, the A algebra is really tiny. But as soon as we have gauge symmetry, then this space of maps gets really interesting. when we didn't have gauge symmetry, the entire space of maps just collapses, and gives us the simple result over there. And so I think I have enough to actually give a really simple example of 3D mirror symmetry now. So
this is connected to BFN?
Hmm?
This is an interpretation of BFN?
So the things I've been saying about state operator correspondence and stacking disks is interpretation, but this is their construction. So yeah, I mean, they say it a little less geometrically and a little more algebraically, but it's this space. So so this thing is sometimes even called the BFN space, and yeah, and so yes, initially Nakajima and then BFN discovered that the cohomology of the space, homology of the space, had the right properties to match some physical things, indices that had been computed, and so they just conjectured that this should be functions on the Coulomb branch, and that was they quite remarkably. It just worked, and matched other physical analyses, and there's, like I said, there's subtleties and things that don't quite match here, which one has to do more to get right. And so, in fact, if you really want to get this from a state operator correspondence, you need to throw in a boundary condition that kills the cotangent bundle, or the cotangent fibers. But yes. Right, so there's this thing called 3D mirror symmetry. So it is analogous to, but distinct from, mirror symmetry in 2 dimensions. It was discovered in examples by Interligator and Seiberg, and using brain constructions by De Boer, Huriyo, Guri, and Oz. So it's the statement. It's going to be kind of vague. So some 3D gauge theories come in pairs. I mean, it's as vague as saying that 2D mirror symmetry relates pairs of Calabi-Yaos. Not all Calabi-Yaos have Calabi-Yau mirrors, but some, and in fact many 3D gauge theories have gauge theory mirrors. So they're pairs, GR and G dual R dual, such that the A and B twists are exchanged. So everything computed in the A twist on one side matches the B twist on the other side, and vice versa. And the examples include all abelian gauge theories. If G is C star to the R and the representation is C to the N, this is mirror to a gauge theory with group C star to the N minus R and representation also C to the N. Nakajima quiver varieties of type A. So those come with a group and a representation, and they are mirror to other.
What is it that?
Sorry?
Do you need to tell us how G acts now?
I do, and I'm not going to. I'm running out of time, and I think that if you want to know, I'm happy to say so. So Nakajima quiver varieties are mirror to other A-type Nakajima quiver varieties. Like it's not mysterious. Sorry, in both cases, there's a prescription. The mirror prescription here is from Hanani and Witten, and uses brain constructions. And finally, a non-example, which is the one I'll actually compute. Pure gauge theory does not have a gauge theory mirror, but has a sigma model mirror. To a space that's maybe familiar in geometric representation theory, one takes the cotangent bundle of the Langlands dual group and reduces by the nilpotent subgroup, or the unipotent subgroup on either side at generic co-character. Finite dimensional space. And right, so now so in this case, there's no mirror gauge theory, there's a mirror sigma model. This is smooth. This is a smooth hyperkähler complex symplectic. And one can compute some things. So let's
You
check
didn't
those
specify in
operators.
any of those examples what the trimanifold is. Is this supposed to work for all trimanifolds?
This is local structure. So I don't need a 3-manifold. I can just talk about R3. And the mirror property of the theories is orthogonal to what sort of space-time they're put on. So yes, this is supposed
It's just all about
to
local
work.
operators.
Yes, and it's in the last like 2 minutes of the talk, it'll be about line operators, but this is supposed to work on all 3 manifolds. Yeah. So on the G side, let's if we take what's been written on the board and as a sanity check, compute. So in the B twist of pure gauge theory, I had claimed that local operators were formed out of gauginos and produced the homology or cohomology of G. In the A twist of pure gauge theory, there's the BFN construction, which is something slightly simpler in this case. It's Borel-Moore homology of the affine Grassmannian for G quotiented by G defined over Taylor series. On the sigma model side, the B algebra, let's do the A algebra first. The A algebra is cohomology of the space itself. And in this case, everything contracts back to G dual. And so we find cohomology of G dual. And these thankfully match. And the B algebra is functions on the space itself. And these also match. And this is the left-hand side is a convolution algebra is equal to the right-hand side as an ordinary algebra of functions by Biazukhovnikov, Finkelberg, and Yurkovich. That's another famous statement in geometric representation theory that's been used a lot in this stuff. Okay, so that's how local operators work. I wanted to say things about line operators and ideally boundary conditions. I think I will say things about line operators and stop for anyone who wants to leave. Line operators are dimension 1 objects. physically there are some operators supported on a line that can be inserted in correlation functions. So line operators form braided monoidal one category. Or more precisely, because we're in this homological TQFT setup, slightly better is an E2 monoidal one category. Call it C. It's so the reason is the category. Also, this is in TQFT terms, it's Z of S1 because there's an S1 linking the line. The reason it's a category is because given any two line operators, one can ask what is the space of interfaces between them? What's the space of local operators that consider their junction? And that's Hom. So Hom between L and L prime is all local operators, the vector space of all local operators that can sit at the junction, rather the cohomology of that. There's a tensor product that comes from putting two lines very close to each other, and there's a braiding that comes from braiding. So if we have L and L prime, we can braid them. This is some local operator in endomorphisms of the tensor product. Moreover, there's a canonical object. I will actually finish in 4 minutes. There's a canonical object one. That's just the trivial or the empty line. And I call it one because it's the tensor identity. A nice feature of the trivial line is that local operators on it are just local operators in the bulk. And so endomorphisms of one recovers the algebra of local operators in the bulk. And so whatever these categories are, and I'll give you mathematical proposals for them in a second, they had better recover all of the previous stuff that has been on the board. So how do we actually find them? Well, physically, I would do circle compactification. I take this S1 literally and rewrite the theory in the presence of a line operator as a two-dimensional theory on a half space. Compactify in S1, I get a two-dimensional theory on a half space where the target of the 2D theory is the loop space of the original 3D target. And in this process, the A twist in 3D becomes an A twist in 2D, the B twist in 3D becomes a B twist in 3D. And one gets proposals for these categories. They look sort of like the Fukai category of the loop space, or coherent sheaves on the loop space. These are horrible, well, the first in particular, the Fukai category on the loop space, is a horrible thing to work with. There is some assistance in that there's also a potential around whose critical points are constant loops. Anyway, one can take that and massage it a bit. And at the end of the day, we have mathematical proposals for what these things are. Phil, Sang-Yu, and Justin also approach this, and what I'm going to write down is actually due to them, approach this from a slightly different angle involving holomorphic topological twists. Anyway, everything more or less fits. And so one version of what these categories are is the following. So CB, and I'll just give you the gauge theory statement. So for group G and representation R, the B category, we think, is quasi-coherent sheaves on. I'm hoping at least part of the audience will know what I'm talking about. So it's maps from a formal punctured disk into R mod G. This formal punctured disk is just an algebraic version of the circle. And there's a potential that localizes to constant loops, which turns this into a Dirac stack. I'm not going to define that. I will say that there is, so one, the identity object is the structure sheaf on constant loops. It's the structure sheaf on maps from D. So on mod G, which is constant loops, and if we localize, if we look at the category that talks to one, if we localize the category at the trivial line, we get something simpler and maybe hopefully more familiar. It's just sheaves on the cotangent stack. It's sheaves on the Higgs branch. Physically, this is where Wilson lines sit. So in this simpler version, one is literally the structure sheaf, and the structure sheaf can be decorated by choosing any representation of G and twisting by it, changing the equivariant structure. And there are things in physics called Wilson lines that take representations of G and define a line operator. I'm not going to write it down. And there's an A category where constant things and holomorphic things have been swapped. So the algebraic proposal for the A category is D modules on the algebraic loop space of R mod G. The trivial line is in slightly abstract notation. It's supported on maps from the actual disk, the non-punctured disk, into R mod G, so two quick things to say about this. One can compute. Well, first, one can compute in this category. Endomorphisms of one reproduce the A algebra in the BFM construction. And then a physics thing to say, this contains vortex lines. Vortex lines physically are given by specifying a meromorphic singularity in the connection of the fields at a line. It's a meromorphic singularity in the transverse plane. And such singularities get associated to slight deformations of one. So I actually like, despite my talk, I really like to compute things and look at examples. And it's quite fun to check in simple examples that vortex lines really do map to Wilson lines across mirror symmetry. And so here, I will stop here and take any questions and continue on for anyone who likes, but thanks.
I've asked Justin, so I'll ask you too. How close does this come? How deeply does this bite into line length?
Oh, fantastically close.
Can
Sorry.
you repeat
so,
that? Ron, please, can you repeat your question? Couldn't hear.
He's going to answer it.
Well, I took the question to be like, how close is this to Langlands, or yeah. So, sorry, this equivalence really looks a lot like Langlands. If we were to
Local.
yes, exactly. If we were to replace this formal disk with a Riemann surface with a curve, this looks like Langlands. And so I think the most important relation comes from considering boundary conditions of four-dimensional theories. So in 4 dimensions, there are A twists and B twists. So Langlands has to do with 4D n equals 4 super Yang-Mills. And given 4D n equals 4 super Yang-Mills with gauge group F, one can attach any 3D n equals 4, any 3D n equals 4 theory with flavor group, with flavor symmetry F. And by flavor symmetry, I mean F has to be, in terms of the gauge theory, you consider the normalizer of G in the symplectic group acting on R plus R dual. F is a thing that acts, let's say this very roughly, acts on R plus R dual independent.
You're just commuting with G, right?
Commuting with G. Let's just, it's, yeah, exactly. There are A and B twists in Langlands that induce A and B twists of the boundary. The boundary line operator categories are modules for the Satake category or its mirror. It's not quite rep G, but or rep F. It's the Wilson line category in the bulk. And one can throw in boundary conditions and all sorts of stuff. But this talks very closely to Langlands. Moreover, S duality in the bulk induces mirror symmetry on the boundary. And so, in fact, the easiest way to identify the mirror of pure gauge theory in 3D is to build a sandwich. Produce pure gauge theory as a sandwich of 4D Yang-Mills with very simple boundary conditions and find its S dual. So very close. The fact that the A twists in the bulk, A and B twists in the bulk become A and B twists on the boundary is really reflected in this statement. So these are solutions of equations of motion on curves. Here they happen to be formal curves, and I'm describing boundary line operators, but the same sort of solutions of equations of motion come up in.
How does
in
R appear in the 4-dimensional gauge theory?
Sorry?
R. What is R in the 4-dimensional gauge theory?
Oh, R is always the adjoint representation in 4D gauge theory. sorry, that's what's going to give you, on this side, it'll give you Hitchin systems.
But if you take any representation with a vanishing beta function, it will still work? Or?
No. For 40 n equals 4, you have no choice.
You really need to join.
Well, wait, but if you talk about a Wilson line or something like that, you can decorate by a representation,
Yes,
which doesn't have to be the edge, right?
agreed.
So-
Sorry, so no, but just the
Yes, I
the represent, like, if you're trying to do some sort of, so there's, in 40, there are, you can, here I was compactifying the 3D theory on S1, which I thickened into a disk. I can compactify the 40 theory on a surface, and I get a category the same way. But these sorts of spaces in 40 involve the adjoint representation necessarily. Otherwise, yeah, sorry. So there's also a category of Wilson lines in the bulk, like in this construction. If there's flavor symmetry in the 3D theory, then the Wilson lines for the flavor symmetry will act by tensor product with the category of lines in 3D. In other words, you can take any gauge Wilson line and tensor it with the flavor Wilson line, is the physics of that. Similarly, you can take any vortex line and tensor it with a flavor vortex. And that's an action of the Satake category on these guys. Also, finally, there should be 2 categories around corresponding to boundary conditions. They're really hard to access, except in the B-twist of sigma models.
Just in the B-twist. They're easy in the B-twist.
Other questions? So, thank Tudor.